Hi everyone. In this lecture, I will give you the definition of an n by n system and also the solution for such a system. And of course, I will give you the basic terminology related to this n by n system and its solution. In addition to giving the definition of such a system and its solution, I will also talk about what a matrix is and how can we convert such a system of linear equations into the what is known as matrix form. And finally, in the end of this lecture, I will also give you the both definition and the example of what an upper triangular matrix is, which is very important for us in the later process in the next lecture. Okay, after summarizing what we expect to see in this lecture, let's start with the basic definition of a more generalized systems of linear equations called an n by n system. And as you might all remember, in the previous lecture, in the very first lecture, I give you the definition of a 2 by 2 system and show you how to solve such a system by simply applying element-wise additional subtraction. And also, I mentioned about what a solution is to such a given system and what kind of alternatives do we have when we are looking for a solution, along with, of course, its geometric interpretation. Now, we generalize our idea to the more general case where we have an n by n system. And by saying n by n system, what I mean is this. We have m different equations and n different unknowns variables, n different unknown variables, namely x1, blah blah, xn, and we have m equations. Okay, let's start. Okay, here's the basic definition of an n by n system. a11 x1 plus a12 x2 plus blah 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 a1n xn is equal to b1, and this is the very first equation. If I number them, say this is the first equation, and right below the first equation is the second one. Yeah, I just number the equations by starting from top to bottom, making my way from top to bottom, and say this is the number m, in other words, the mth equation. How do I understand that? I just look at how many different equations are given to me in this definition, and if I count the number of different equations, I see that we have m different values on the right hand side, so that means we have m equations. Okay, and we have also n unknowns. And what are the unknowns here? If you notice that we have x1, x2, and xn, and this tuple, this x1 to xn tuple, is called the unknown variable vector, right? This is just a vector of unknown variables. And as you might notice again, in right below the first equation, in the second equation, we have the same unknown variables, which is very normal to see, right? Because what we will be looking for would be these values. And in all of these equations, we have the same unknown variables, because this is what we are trying to find. Right. So, x1, blah blah blah, xn are called, these xi values are called the unknown variables. In other words, what we are trying to find. Unknown variables. This is the most important, maybe the most important part of the terminology of system of linear equations, since we will be trying to find these values, right? Okay, how about the aij's? Look at these values. In each equation, right to the left of each unknown variable, we have some coefficients, and maybe that would be better if I write them or circle them in different colors, just to make you to be aware of this difference. Let's see, the ones that I circle in red You see, these are the coefficients, and these are called the coefficients, guys, right? So these are the coefficients. In other words, the values in each equation which are placed right to the left of each unknown variable are called the coefficients, as I indicate them in red. And how about these are of course the basic terminology, as I said earlier. We call the xi's as unknown variables, we call the aij's, and let me write it down just to show you clearly. Yes, these are the coefficients, right? These are the coefficients of the unknown variables. Okay, and how about the bi's, right? On the right hand side, these are the right hand side values. Let's use a different color, a mixed one, maybe, right? And the values, the bi's, in other words, which are on the right hand side of each equation, are called the right hand side values, or the known values, shortly, right hand side values, we call them. Okay. And again, we call this system, or such a system, an m by n system, because why? Because m represents, or in other words, m corresponds to the number of equations, right? The number of equations, right? M represents the number of equations, whereas n represents the number of unknown variables. So that's why we call such a system as an m by n system. Okay. The number of equations is represented by m, and the number of unknown variables is represented by n. Okay. And let's define another important concept, which would be, of course, what we'll be trying to find. An n-tuple, right? We try to find such an n-tuple. In other words, a vector of x1 to xn which satisfies all the equations in this given system. And such an n-tuple is called a solution, or a solution set. In other words, an n-tuple x1 blah blah xn that satisfies both equations simultaneously is called a solution, or is called the solution set of this system of linear equations. Well then, what are we trying to do here? So we will try to find such an n-tuple that satisfies each of the equation simultaneously. So if we assert that an n-tuple is a solution, it must satisfy all of these equations given in the system at the same time. That is, of course, not very simple. Let's see. This is actually one of the main reasons why I start with the simple case of 2 by 2 system. If you remember from the previous lecture, I showed you what a solution is, what are the possible alternatives, what does it mean from geometric point of view, and how can we solve such systems. We started with a simple case. Why? Because actually I wanted to show you many different things, as I pointed out in the very first lecture. Here's the thing. First of all, I will remind you this case and then keep going with the more difficult ones. Okay, suppose this is a system, it's a 2 by 2 system, and when I use or I apply elementary operations, you see, element-wise addition or subtraction, x2's are cancelled, and what we got here is that 2x1 is equal to 9, and what I am trying to do here is if you notice, in the original first case of the given system, we have 2 equations and 2 unknowns, but applying elementary operations, for instance, adding them term by term. Now what we have is a one equation and one unknown variable, which is the base case to solve an equation with unknown variable with the number of 1, right? We have just one number. We have just one unknown variable here. So by simply dividing both sides by the coefficient of the unknown variable, which is 2 in this case, we got the value of x1, right? Which is nothing but 4.5, 4.5. And then if you plug this value back in one of these equations, we got the other value, which is x2, which is the other unknown variable, right? And in this case, it would be minus half, right? 0.5 or minus half. Don't forget negative sign, right? If you plug it back. So what we're trying to here, actually, what we try to do is we eliminate the number of equations and unknowns by applying some operations, arithmetic operations, in order to obtain a system which is much more easier to solve. So if we have a 2 by 2 in the beginning, if we eliminate one equation and one unknown variable, then we have only one unknown variable and one equation that we can simply solve. Okay, why did I mention about this again? Because, you know, now we have much more complex situation. We will not have just two equations and two unknown variables, but a simple observation that we have made by taking into account the solution of such a simple case where we have only two equations and two unknown variables. We can generalize this idea to a more general case where we have m equations and n unknowns. So in other words, if somehow we are able to eliminate these equations or the unknown variables from an n by n system to a 1 by 1 system where we have only one unknown variable, we can simply solve. And then by using back substitution, in other words, when we find one of the unknown variables and plug it right one step above it and find the other unknown, and then repeating the whole process until we have reached to the solution, in other words, finding all of the unknown variables, we can solve the system. But how can we do that? So we need a much more technical method to somehow convert our original system into that of one that we can simply solve by using back substitution method, just like we used here in the 2 by 2 case. Okay, I'll come to that point later on in our next videos, but for the time being, let's just skip this point and let's see how can we write the same system of equation, what is known as in the matrix form. I will try to write this system in the matrix form because if I do that, that means I can apply any operations that I can do on a matrix, on a given matrix. But how can I do that? What I need to find a way to represent such a given system, like that of this general case where we have n by n system, and I will try to convert it into the matrix form. Okay, let's see how can I do that. And before even that, let's first define what a matrix is, because I need to know the definition of a matrix before I start converting this system into a matrix form. And a matrix is nothing but a rectangular array of numbers that are arranged in rows and columns, and which means that an n by n matrix is nothing but a rectangular array of numbers where m is the number of rows that I write here horizontally until I reach to the very last row, and n is the number of columns that I write vertically within the matrix form. Right. This is called a matrix, and this representation corresponds to a matrix. And suppose the name of the matrix is A, we can write technically a matrix A in such a way: A, I, J, which means that all of these Aij's are the entries or the values of this matrix, but they are arranged in such a way that I corresponds to the row number. Okay, I corresponds to the row number, and J corresponds to the column number. It is just like putting the address in this entry, because if you know both the row number and the column number, then the value that is placed at the intersection of these two numbers, two index numbers, is the value we are looking for. What I mean is this. Let's move it a little below and continue to our reasoning. Suppose this is the matrix A. Okay, 3 minus 4, 7. Okay, and let's make up some values. 1, 0, minus 1, 2, 1, 4. Okay, suppose the matrix A is given like this. So we have in this case a 3 by 3 matrix. How did I just understand that? Well, because we have 3 rows, right? If I look at the matrix from top to bottom and count the number of rows, this is the first row, from top to bottom, this is the second row, and this is the third row. And if I count the number of columns, or if I label them from left to right hand side, this is the first, this is the second, and this is the third column, right? This is the first column, this is the second column, and this is the third column, right? So we have a 3 by 3 matrix here. In other words, a matrix that has 3 rows and 3 columns and have 9 entries. Let's say 9 real values. Okay, it's just numbers. The entries of a matrix are just numbers, but nothing. So if I want to find the value A23, then what? Then what is this? How can I find this value? As I pointed out earlier, right above, if Aij corresponds to the values of matrix included, then I corresponds to the row number, which is the second row. So I will look for the value which is in the second row and the third column. What I mean is this. I look through the rows and find the row number 2. And you see this is the second row, the middle one. But where it intersects with the third column, right? And look at this value here. This is the value that I am looking for. Maybe it would be better to again write it in a different color, because this is what I'm looking for. This is A23, the entry in the second row and third column, right? So for instance, if I look for the entry 31, then what I am doing is I find the third row and look the value where it intersects with the first column, and in this case this is the third row and this is the first column, and the value that is placed at the intersection of this 2 index is 2, right? So A31 entry is equal to 2. This is what a matrix is. So in short, a matrix is nothing but a rectangular array of numbers placed in rows and columns, and the number of rows and the number of columns are represented with the index values as I showed here, and if I mean aij, I mean I is the row number and j is the column number. Okay, now after defining what a matrix is and how it is represented, let's get back to our point, because here of course it's important for me to understand what a matrix is, but the more important thing is that I need to convert my system into the matrix form. Okay, how can I do that? In other words, I can somehow find a way to represent both coefficients and right hand side values in the same matrix. Okay, let's do that. Here is the plan. And one more thing, of course, before even doing that, maybe you understand why I write the equations coefficients. Well, in other words, why do I write these coefficients in the aij form, like you see a11, a12, a1, and the second equation is like a21, a22. This somehow might give you a clue about why I write them like this, because you know I can use arbitrary numbers like alpha 1, alpha 2, alpha n, or beta 1, beta n, gamma 1, something like that. Any real coefficient that can be used. I could have used all of them. Okay, but I used, you see, a more arranged system of coefficients, a11, and if you notice, we also define the index values in the same manner. What I mean is this: for instance, what are the values of the first row? Only first row. If I want to write only the first row, the elements on the first row is like a11, a12, right? And a13. Why? Because the row number is 1 and the column number is arbitrary. I'll just read from the left hand side all the way to the right hand side, right? So 1, 1, 1, 2, and 1, 3. In other words, here is the thing. I write the coefficients of each unknown variables in the matrix in the given order. And let me erase this because I will expand the right hand side just a few seconds later. Keep going. This is actually what? These values are the coefficients of the first equation, right? We observed it, right? Let's again go up a little bit. See the first equation and look at the coefficients of the unknown variables in the first equations. These are a11, a12, and a1n, but nothing, right? So again, this just goes and goes on until we reach to the last coefficient, right? And for the second equation, I do the same. So just write the coefficients of the unknown variables in the second equation, right? Until the last one. So in other words, the first row in this matrix corresponds to the coefficients of the first equation, and the second row corresponds to the coefficients of the second equation. And okay, the first row corresponds to the first equation, and the second row corresponds to the coefficients of the second equation. And with this strategy in mind, I write the coefficients of the unknown variables in the very last equation, which is the mth one, right? And the most right hand side, the value on the most right hand side is the amn. Okay, these are all the coefficients. Okay, but is it enough? I know there are n unknowns, right? Since there are n unknowns, there should be n coefficient values in each row, but this is not enough for us to represent all the system. We have one more thing. If I write only this is called the coefficient matrix. Okay, if only this is written, we call this matrix the coefficient matrix of the system. Why? Because we have only the coefficients of the unknown variables in an arranged order. In other words, the values in the first row correspond to the coefficients of the unknown variables in the first equation, and the second row corresponds to the second equation, and in this manner we got the coefficients of the mth, the last equation, in the last row. Okay, but as I said, this is not enough just to represent all the system. We have one more thing. What we have not written so far is that, okay, if each row matches with the equations coefficients on the left hand side, but then where will I plug the values of the right hand side in this matrix, right? We have also right hand side values, as I mentioned earlier, bi's, right? b1, b2, blah blah, bm. Then where are they? Yeah, this is the missing point up to this point, and let's complete this missing point. Okay, and what I am doing is, now I will expand this matrix a little more with the values that I know on the right hand side, which are nothing but the bi values. So this is b1, this is b2, blah blah blah, and this is what? This is bm. Okay, that's excellent. And this matrix is now called augmented matrix. Augmented matrix. Why it's called augmented matrix? That's because we've just expanded our coefficient matrix by inserting the right hand side values to our matrix to represent our system in the matrix form. And what we will be using, doing Gaussian elimination method or Gauss-Jordan method, which are much more technical methods, of course, we will use this matrix. This is the matrix that we will be using by applying these techniques like Gaussian elimination or Gauss-Jordan method. So now, as you might notice, each row represents one equation. In other words, the first row is actually corresponding to the first equation, whereas the second one corresponds to the second equation, and in this way the mth row corresponds to the mth equation, and we got an m by n matrix as required, right? As desired, because our system is an m by n system, and if this matrix form really corresponds to that system, they should match, right? The size should match. So we got m rows and n columns, which enable us to represent our system of linear equations in the matrix form. And what I've done is here is called the matrix form. So this matrix, this augmented matrix, is the way that we convert our system of linear equations into that of a matrix called an augmented matrix. All right, let's continue. So up to this point, guys, what I've done, we know what an m by n system is and the basic terminology. We know what coefficients are, what unknown variables are, what is the right hand side values, and what we're trying to find, and what is a solution of such a system, and how can we find that, and what is a matrix, We know what a matrix is and the basic terminology related to that. And we know what an augmented matrix is, right? Coefficient matrix and augmented matrix is if I raise the right hand side values from this matrix and keep the remaining, then we got a coefficient matrix. But if I expand my matrix with the right hand side values, then I have an augmented matrix, which is actually nothing but a representation of our system of linear equations in the matrix form. And this augmented matrix is my matrix form that I use for solving a system of linear equations. I apply my operations on such a matrix. Alright guys, so let's get back to my basic point. What was our main goal prior to the start of this lecture is that, you know, whatever we do, we're trying to solve such a system, which means now we will most likely have something like this. For instance, 2x1, we will try to solve this kind of equations. For instance, 3x plus 4x3 is equal to minus 7, right? 3x1 minus 7x2 minus 5x3. But let me say that these are just arbitrary values that I make up. So it does not need to be, our system does not need to be like this. You know, there are many different systems that we need to solve. I'm just making up the values to show you how difficult to solve such a system. Even in this case, where we have, suppose, 3 equations and 3 unknown variables. By the way, guys, when we have a system where the number of equations and the unknown variables are equal, we call the system a square system. It's just an n by n system, because if the number of equations is equal to the number of unknown variables, then we have an n by n system, right? It's simple to understand that, but let me notice you about that. Okay, now what we have? We have a 3 by 3 system. How do I understand that? Because we have 3 different equations, right? They are all linear equations. This is the second equation, and this is the third equation, right? 3 different equations and 3 unknown variables. We have x1, x2 and x3. So if we are required to find the solution of this system, actually what we are trying to do is we will try to find such a 3 tuple, namely x1, x2 and x3, such that this 3 tuple must satisfy each equation simultaneously. So now it is not very simple, because even if in this 3 by 3 case we need to somehow eliminate one of these equations along with the associated unknown variables, so that reduce the system to 2 by 2, and then from 2 by 2 to 1 by 1, right? This is the method of elimination, because when we have a 2 by 2 system, right, if you want to reduce it, what we've got is a 1 by 1 system. In other words, one unknown and one equation. But if we have a 3 by 3 system, then we need to first reduce it to the 2 by 2 size, and then 1 by 1, right? So that we can find the solution of the unknown variable included here, and then substitute it back in the equation where we have one more equation or unknown, and find the value of the other unknown, and then after finding 2 of the 3 unknown variables, then plugging it back where we have 3 unknown. But in this case, since we already have found out what the other 2 variables are, now we have only one unknown variable and find the solution to our system. Okay, this is the actually plan. But The difficulty is, how can we do that? In other words, we should find a method or a technique that would enable us to convert our arbitrary n by n equation system into that of very simple one that we can simply solve with one unknown variable and an equation, and then plug it back or substitute it back into the other equations and find the all unknown variables. Right. The technique that would be using for solving such a system is like, starts with, maybe there are many methods, but we can start with the Gaussian elimination and Gauss-Jordan method, and then Kramer method, and there are many methods that are possible that we can solve this equation. But even before that, let me show you one important point or a key observation that we can make, because to understand what we are doing, as you see, now our problem is to solve such a system. And even worse, if we increase the number of equations and unknown variables, suppose if there are 5 equations and 5 unknown variables, then it would be more complicated. And even if we have, you know, as it increases, the complexity of this of finding the solution would also increase, right? If we have 10 equations and 10 unknown variables, then it would be even more complex. So we should need a more convenient method or a way in order to solve the system of our linear equation. In other words, and a way to find such an n-tuple that must satisfy each equation at the same time. Okay, but as I said, before I mention about and show you how it is done by using, in other words, how it is solved by using a Gaussian elimination, I would like to give you the result of one simple observation. Let's look at this equation, for instance. Suppose here is the system: 3x1 plus 4x2 plus 7x3 is equal to minus 5. Okay, 5x2 minus 6x3 is equal to 4, and 9x3 is equal to 18. Alright, so suppose this is a system that we are required to solve. In other words, what does it mean to solve such a system? We have a 3 by 3 system, right? Beforehand, how did we understand that? Because we have 3 equations, right? If I again number them, this is the first equation, this is the second equation, right? From top to bottom I number them, and this is the third equation. So we have 3 equations and 3 unknowns, because we have x1, we have x2, and we have x3. So finding the solution of such a system means that we are trying to find such a 3 tuple like x1, x2, x3 that satisfies each equation, right? Concurrently. Each equation must be held by this vector of values of xi's. Okay, but look at the system of equations that I've just written for you. I do it on purpose. There's one thing, that's a key point here. There's a very important key point here that we should take away with us before completing this lecture. But the thing is, you see, look at the system. In the last equation, what we have? If you notice, we have only one unknown variables, right? The other unknown variables, x1 and x2s, are cancelled out here. Actually, they are here, but the thing is, this is the way: 0x1 plus 0x2 plus, right? They are here. but their coefficient is 0. If you take the coefficients of these unknown variables, then these values what? These values would be equal to 0, right? And the same thing is true for the for the second equation, right? For the second equation, and there is the 0x1 here, right? But if you take the coefficient 0, then this is equal to 0. So if you notice, 9x3 is equal to 18, and dividing both sides by 9, what do we got? We found the value of x3. That's very important. We simplified one of the unknown variables using the third equation, right? So x3 is just 2. But then what? Look at the second equation. In other words, the equation right above the last one. We have now x2 and x3, right? There is no x1 here. And we have just found the value of x3. So, plug in the value of x3 in the second equation. You see what we have? In the second equation, we have 5x2 minus 6 times, since the value of x3 is 2, 6 times 2 is equal to 4. And in this equation, as you notice, the only unknown variable now is x2, and since there is only one unknown variable, we can again solve this equation, because this is just a one by one system, right? It's just as simple as solving a one by one system where there is only one unknown variable and one equation, and all the other values are known. So we have 12. If we move it to the right hand side of the equality, it was minus 12. So now it is 16. 5x2 is equal to 16, and x2 is what? 16 over 5. That's the solution. 16 over 5, which is nothing but, if you want to use decimal point, 3.2, right? We can find it. Okay. Now, we know the values of x2 and x3. So, in the first equation, since we know the values of x2 and x3, what is the only unknown value that we don't know? That's on x1, right? Because we know what x2 and x3 are. So just substitute the values we have found for x2 and x3 back in the first equation. We got 3x1, okay, plus 4 times 16 over 5 plus 7 times 2 is equal to minus 5. So I just plug the values back in the first equation, right? To find the last unknown variable, which is x1. So we got 64 over 5 right here, and we got 14, and on the right hand side we got minus 5. And after this is just an elementary high school knowledge about solving an equation in one unknown variable, right? So if I, let's see, denominator, if I multiply the denominator here by 5, we got 70, and then 134, and minus 5 minus 134 over 5, right, is equal to 3x1. And again, do the same thing. We equalize the denominator by multiplying again, because the common denominator. If we add or subtract those values which don't have the same denominator, we just equalize the denominators and then do the other arithmetic operations, right? So 25 minus 25, and here we got minus 159 over 5 is equal to 3x1, and dividing both sides by 3, which is the coefficient of the only unknown variable, we got what? We obtained the value of x1, right? The last unknown variable left behind. So this is 159 over 15. If I have not made an, of course, numerical mistake, perhaps not, I haven't. Okay, this is the last unknown variable. So what we have found, again, you see, this was the form that the system is given, and since we find the value of x3, then substitute back in the second equation, and then finding x2 and x3 and substituting that values back into the first equation, we have found all the values of equations. Now we have the solution, right? Then x1, x2 and x3, we were looking for that solution, and here's what we got finally. Here's the solution. Say this is the x, and x1 is minus 59 over 15, right? This is the value of x1, and x2 is 3.2 and x3 is 2. In other words, this is the three tuple that we are looking for, right? This is the three tuple that we are looking for. So in other words, the solution to the given system of linear equations. Okay, I started with this kind of system. I'm saying this kind of system because if you notice that it has already been eliminated. That is what made me to solve this equation in a very simple manner without using any technical methods such as Gaussian elimination or Jordan or Kramer or so on. The reason for that, because due to the way the last equation is given, I can simply find one of the unknown variables, and in the second equation there is only one unknown variable again, and in the first equation, since I found the other values in the meanwhile, still there is only one unknown variable, and I simply solve this equation. Okay, but this is a spatial case, and here's the key observation. Now let's get back to my point. Suppose we have this kind of equation, right? Suppose this is the system given. Well, let me point it out like this. Is a different color to bring your attention. Now look at the system that I surrounded by a red box. There is no elimination here, you see. All the coefficients are different from 0. Okay, so what can I do about such a system? Here's the key observation. If somehow I'm able to reduce this system into a matrix form that is similar that of this equation I've just solved, then it would be very simple for me to solve or to apply the same strategy, right? In other words, given an arbitrary n by n system, how can I convert such a system into this kind of system, which we will call a triangular system? Alright guys, let's finish this by defining what a triangular system is technically. Here's the thing. Suppose I have a matrix. And this is the matrix. right? That's the, let's say this is the matrix. And let's give the augmented matrix. Okay. And how would I understand this is an augmented matrix? This is the thing. If we use an augmented matrix, we use a vertical line like this, and this is the way we represent an augmented matrix for a given system of linear equations. And the values here right to the left of this dashed red line, vertical red line, right to the left of it, are the coefficient values. Okay, so since there are 4 coefficient values, that means we have 4 unknown variables. Okay, 4 unknown variables, and the values that is right of the vertical dashed line I just draw here, you see, these values are called the right hand side values, and this matrix again is called the augmented matrix. This is the way we represent our augmented matrix. In other words, the matrix form representation of our system. So what I understand from here, since we have 1, 2, 3 and 4 rows, we have 4 different equations, and we have 1, 2, 3, 4 columns, besides the, of course, right hand side. I don't count it because they represent the right hand side values of the equality, right, of each equation. So we have 4 equations and 4 unknown variables. This is the augmented matrix version of our system. In other words, if I want to write this, or in other words, if I want to convert this matrix into the system, then what? Say this is actually 3a, because 3, 4, 7 and 6 are just the coefficients in the first equations, right? The coefficients of unknown variables, and I just write some unknown variables, call them a, b, c, d, alright, is equal to 7. So the first row is actually corresponds to the first equation like this: 3a plus 4b 7c plus 6d is equal to 7, right? I convert the first row to the first equation. And how about the second row in this manner? So we got, you see, the coefficient of the first unknown variable is 0, so there is no value, so 9b, so make sure you write the equation correctly, minus c, right, because we have minus 1 and 2, so we got 2d is equal to minus 1. And in a similar manner, now you got 2 zeros, so a and b's coefficients in the third equation are equal to 0, so we got 7c plus 3d equal to 3. And for the last equation, you see the coefficients of the all 3 unknown variables in the last equation, in the fourth equation, are equal to 0, so 0a, 0b and 0c, but the coefficient of the unknown variable d is different than 0, so we got what? We got 6d equal to 4. So actually, you see, this is the third equation, and this is the fourth and the last equation. In other words, we converted, if we are given an augmented matrix, we can simply convert it into its system equivalent form, right? And vice versa, if we are given a system, we can convert it into its augmented matrix form. And you notice there is 0, 1, 0, there is 2, 0 here, right? We can add the addition symbols, plus symbols, 0 plus 0 plus 0, right? These are the coefficients of A, B, C's. Then what I am trying to point out here is that the entries that I just now draw, starting with the upper left corner and making my way down to the all the way down to the right corner below in the last row, these values on this diagonal are called the diagonal entries, and this line I just drew for you is called the main diagonal, right? And what an upper triangular matrix is, which makes us, of course, to compute the solution set of a system, is that below the main, if we have all zeros below the main diagonal, then we have an what is called an upper triangular matrix. And technically, if I want to define what an upper triangular matrix is from a technical point of view, I say this: for all A greater than J, if, let's start with if, conditional, if for all I greater than J, if you notice that strictly greater than, okay? In other words, the main diagonal elements are not included. We concentrate on the values of the entries below the main diagonal, right? Below the main diagonal. If they are all 0, then it's called an upper triangular. And technically, which means if for all I greater than J, if we have Aij is equal to 0, then this kind of matrix is called an upper triangular matrix. Upper triangular matrix. Upper triangular matrix. And it is very important for us to know, because if we are somehow able to convert our system of linear equations into that of a upper triangular one, right? Into an upper triangular system, then we can simply solve our system. This is the strategy that we will stick with while trying to solve our system using Gaussian elimination or Gauss-Jordan methods, which are of course much more technical methods. Okay, so guys, the matrix I just show you here is an upper triangular one. Why? Because I look at the entries below the main diagonal and they're all 0. And if you notice that we have a kind of staircase ladder of zeros. In other words, in the second row there is 1 0, but in the third row, in other words, one row right below it, we have more zeros than the one above it. And in the fourth row, in the last row, we have one more zeros from the one right above it, right? 1 0 in the second row, 2 zeros in the third row, and 3 zeros in the fourth row. And if you notice that we have a kind of increasing number of zeros as we make our way down to the last row. So I will define this property from a much more technical point of view in the next lecture, when I start to talk about elementary row operations. And of course, even before that, I will show you what it means for two systems to be equivalent. In other words, what does it mean for two systems of linear equations to be equivalent in terms of solution set. And then we will try to convert one system into its equivalent form and see if it is possible or not. And how can we do that? Can we convert a system into an equivalent one? And then we will proceed to one of the most important topics, namely elementary row operations, and then combine our idea of upper triangular form, equivalent form, and elementary row operation for applying a Gaussian elimination or Gauss-Jordan method for solving a system of linear equations. Okay guys, so far we have learned many things. Let's recap what we got here what we have learned in this lecture, in the third lecture. So in this lecture we learned what a n by n system is and the basic terminology like the unknown variables, the coefficients, right hand side values, number of equations and the number of unknown variables. And then what does it mean for us to find the solution of an n by n system in the more generalized case? And how can we combine the solution, finding the solution of a 2 by 2 system into that of finding the solution of an n by n system? And what a matrix is, we also learned what a matrix is and the basic terminology related to matrix, how to find the entry of a matrix, what is the main diagonal elements, what is the coefficient matrix and what is the augmented matrix, and how can we convert a given system of equations into an augmented matrix or vice versa, right? Or how can we convert a system to an augmented, or how can we convert an augmented matrix into the system form, right? And how can we find the solution of an upper triangular system? And see that how simple is that? Why we started with an upper triangular system? In other words, why we solved such a system? Because it is simple and we will somehow find a way to reduce our system to that of one equivalent to solving an upper triangular system. And of course, last but not least, we defined what an upper triangular matrix is, both technically and both from an application point of view. Alright. So in the next lecture, I will talk about equivalent systems and what does it mean for two systems to be equivalent and how can we convert one system into its equivalent form, and then the elementary row operations and how can we combine our knowledge of upper triangular matrix, elementary row operations to solve a system of linear equations. Until then, have fun and see you in the next lecture, guys.